Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on complex integration in which I will derive higher order derivative of an analytic function. In this lecture I will show you that an analytic function may be differentiated to any order and each order of derivative is analytic. The theorem for higher order derivative of an analytic function is: let function of z be analytic within and on boundary C. Within means inside the points of C, boundary C, of a simply connected region D. This region is known as D region. Then function of z possesses derivatives of all orders and these derivatives are themselves all analytic at the point z equal to z naught. Their value being means nth order derivative B, nth order derivative of function of z at the point z equal to z naught equal to factorial n by 2 pi I integration along the curve C function of z by z minus z naught whole to the power n plus 1 dz. Now we prove this. Since in the previous lecture I have already given that the derivative of an analytic function at the point z equal to z naught equal to 1 by 2 pi I integration along the closed curve C function of z by z minus z naught whole square dz. Let this is number 1. Let z naught plus h, z naught plus h is a point in D, then derivative of function of z at the point z naught plus h equal to 1 by 2 pi I integration along C function of z by z minus z naught plus h whole square dz. Let this is number 2. Now derivative of function of z at the point z equal to z naught plus h minus derivative of function of z at the point z naught by h equal to, here we write 1 by h. Firstly write this right side 1 by 2 pi I integration along the curve C function of z by z minus z naught minus h whole square dz minus 1 by 2 pi I integration along the curve C function of z by z minus z naught whole square dz bracket closed, and this will be equal to 1 by h, here common 1 by 2 pi I integration along the curve C 1 by z minus z naught minus h whole square minus 1 by z minus z naught whole square function of z dz. This equal to 1 by h 1 by 2 pi I integration along the curve C. Here LCM is z minus z naught minus h whole square multiply z minus z naught whole square. Here z minus z naught whole square minus z minus z naught minus h whole square function of z dz. This equal to 1 by h 1 by 2 pi I integration along the curve C. Here we get 2h z minus z naught minus h square by z minus z naught minus h whole square z minus z naught whole square function of z dz. Here we take common h and this h will be cancelled. This will be equal to 1 by 2 pi I integration along C. Here 2z minus z naught minus h by z minus z naught minus h whole square z minus z naught whole square into function of z dz. This equal to we take 2 common here and we write 2 as factorial 2 1 multiply 2 by 2 pi I integration along C z minus z naught minus h by 2 by z minus z naught minus h whole square z minus z naught whole square multiply function of z dz. Let this is number 2. Now derivative of function of z at the point z naught plus h minus derivative of function of z at the point z naught by h minus factorial 2 by 2 pi I integration along the curve C function of z by z minus z naught whole cube dz. This equal to from 2 we get left side factorial 2 by 2 pi I integration along the curve C z minus z naught minus h by 2 by z minus z naught minus h whole square z minus z naught whole square function of z dz minus factorial 2 by 2 pi I integration along the curve C, function of z by z minus z naught whole cube dz. We take common factorial 2 by 2 pi I integration along the curve C, function of z, we take here function of z multiply z minus z naught minus h by 2 by z minus z naught minus h whole square, z minus z naught whole square minus 1 by z minus z naught whole cube dz. This equal to factorial 2 by 2 pi I integration along the curve C, function of z, and value of this is 3 by 2 h z minus z naught minus h square by z minus z naught minus h whole square, z minus z naught whole cube dz equal to factorial 2 by 2 pi I integration along the curve C. Here we take common h multiply function of z 3 by 2 z minus z naught minus h by z minus z naught minus h whole square, z minus z naught whole cube dz. Let this is number 3. Now let us draw a circle gamma with center z equal to z naught such that z naught plus h point lies inside the circle. Let us draw a circle gamma with center z naught and radius rho such that the point z naught plus h lies inside the circle gamma. Since equation of the circle gamma is z minus z naught modulus equal to rho. Again, since z minus z naught minus h modulus greater than equal to z minus z naught modulus minus modulus of h. Let modulus of h equal to half rho. Let this is number 4. Therefore from 4 modulus of z minus z naught minus h greater than equal to rho minus half rho equal to half rho. Let this is number 4, this is number 5. So here we write 5 and this is 6. Since function of z is analytic in D, but function of Z by Z minus Z naught minus H whole square, Z minus Z naught whole cube is not analytic inside the circle gamma, but function of Z by Z minus Z naught minus H whole square, Z minus Z naught whole cube is analytic in the region between C and gamma. Therefore, by using Gauss doubly connected region 3 may be written as, here in place of C we may use gamma. Therefore, left side of 3 is this equal to, in right side we write factorial 2 by 2 pi I integration along C. In place of C we write gamma H function of Z 3 by 2 Z minus Z naught minus H by Z minus Z naught minus H whole square, Z minus Z naught whole cube dz, taking modulus in both sides. We get modulus of derivative of fz at the point z naught plus h minus derivative of fz at the point z equal to z naught by h minus factorial 2 by 2 pi I integration along the curve C fz by z minus z naught whole cube dz, and this will be equal to modulus of this quantity. This is less than equal to factorial 2 by 2 pi I integration modulus of h modulus of function of z 3 by 2 modulus of z minus z naught plus modulus of minus h by modulus of z minus z naught minus h whole square modulus of z minus z naught whole cube modulus of dz. This is less than equal to factorial 2 by 2 pi I modulus of h modulus of function of z is m, because function of z is an analytic function, so it is bounded. This is less than equal to a positive quantity m. Here 3 by 2 rho plus modulus of h by, this is half rho square rho cube and integration of modulus of dz implies that modulus of derivative of function of z at z equal to z naught plus h minus derivative of function of z at the point z naught by h minus factorial 2 by 2 pi I integration along the curve C function of z by z minus z naught whole cube dz, this is less than equal to factorial 2 by 2 pi I modulus of h m 3 by 2 rho plus modulus of h half rho square rho cube and integration of modulus of dz is 2 pi rho, means the length of the circumference of circle gamma. Since radius is rho, so circumference is 2 pi rho, and this tends to 0 as h tends to 0. Therefore, derivative of function of z at the point z naught plus h minus derivative of function of z at the point z naught by h limit h tends to 0 equal to factorial 2 by 2 pi I integration along the curve C function of z by z minus z naught whole cube dz implies that second order derivative of function of z at the point z naught equal to factorial 2 by 2 pi I integration along the curve C function of z z minus z naught whole cube dz. This is the required result for finding second order derivative of an analytic function. Therefore, it is clear that first order derivative of function of z is analytic. First order derivative of function of z is analytic at the point z equal to z naught, means in any arbitrary point its differentiation may be obtained. Differentiation is second order derivative of the analytic function. Now we use the method of induction to get that the analytic function possesses any order derivative. Let it is true for n equal to m. Therefore, mth order derivative of the analytic function will be equal to factorial m by 2 pi I integration along the curve C function of z by z minus z naught m plus 1 dz. We need to show that the theorem is true for n equal to m plus 1. Now, derivative of function of z of mth order at the point z equal to z naught plus h minus derivative of function of z of mth order at the point z equal to z naught by h equal to, here we have 1 by h, we write 1 by h. Here in place of z naught we write z naught plus h. Here in place of z naught, here we have written z naught plus h, and the same thing right side. We take common 1 by h factorial m by 2 pi I, and we write function of z dz. Here we take common z minus z naught, remains 1 minus h by z minus z naught, and whole to the power m plus 1, and we write these things same. Now we write outside 1 by h factorial m by 2 pi I. Here same thing, only we have written this power as negative. We take it as numerator, and we expand this in binomial expansion, binomial theorem. Now we get here that 1 cancel, we take common m plus 1 and h. So here we take m plus 1, and if we take h common, then this h will be cancelled. So here we have no 1 by h, and we write the remaining things. Now taking h tends to 0, if we take h tends to 0, this part will be 0 and other terms will also be 0. Only remains here 1 under this bracket. So here m plus 1 multiply factorial m, that is factorial m plus 1, and here 2 pi I, here function of z by z minus z naught to the power m plus 2, because here we have taken common z minus z naught. So this will be z minus z naught to the power m plus 2 here. Implies that this is m plus 1th order derivative at the point z naught equal to factorial m plus 1 by 2 pi I integration along c function of z by z minus z naught to the power m plus 2 dz. Therefore it is true for n equal to m plus 1. Hence it is true for all n belongs to capital N set of natural number. Therefore theorem is proved. Therefore we see that we are getting any order derivative at any point z equal to z naught. That means in each case we get that any order derivative is an analytic function, and we get the result m plus 1th order derivative. Here in place of m plus 1, if we write n, we get function of z at the point z naught, its derivative nth order equal to here factorial n, in place of m plus 1 we write n by 2 pi I integration along the curve C function of z by z minus z naught to the power. Here we have m plus 1, here m plus 2, one more. So n plus 1 dz. Therefore, theorem is proved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.